video contains your notes for section 2.2. We're looking at infinite limits, limits in infinity, and then a real quick blurb at the very bottom about the squeeze theorem. So what I've done, kind of to save time on these videos, is I went ahead and started filling out some of your notes. So again, I cannot stress how important this is. You need to understand what I'm telling you, and you'll want to write it down as well. So you're probably going to need to pause the video to catch up with me as I'm going through some of these. So feel free to pause it, catch up, write it. Like I said, the good thing about this is in class you're listening and writing at the same time. Now you have the opportunity to listen, pause, write. So it's kind of like you're getting it twice. You're listening to it, thinking about it, processing it, and then you're processing it again as you're writing it down. So I think this is kind of an advantage for you. All right, so infinite limits and limits at infinity. We're going to be looking at a function I'm calling f of x over here. Looks like kind of a crazy function. Limits at infinity means as x approaches infinity or negative infinity. So limits at infinity kind of tells us, if we're looking at a graph, where do I look? So look toward infinity. What's happening to the graph? Find it. Look toward negative infinity. What's happening on the graph? Find it. Where is it headed? So that's what we're doing. So over here, limit as x approaches infinity. So I'm going to, my eyes are going to look way out as x approaches infinity. Where do you think that pink function will be? Well, in my opinion, this pink function looks like it continues to get really, really close to 4. So I think as x approaches infinity, my y's approach 4. Looks to me like there's a horizontal asymptote there. All right, how about the negative infinity? Well, look at the graph. Send your eyes toward negative infinity. Well, my interpretation of this graph is it keeps going. So I believe that my y values are getting really, really, really close to 2. That's where my y values are headed. So, and you can see that there appears to be a horizontal asymptote at y equals 2. These two right here represent horizontal asymptotes. So y equals 4 and y equals 2 are horizontal asymptotes. And I'm going to abbreviate like that. Infinite limits are where the function, where as in an x value, where is the function headed toward infinity or negative infinity? So let's look at this one. Where is the function headed toward positive infinity? The limit as x approaches what? What's the x value that we're getting close to when the y values on both sides? Remember, this is the limit when the y values on both sides are getting close to infinity. I would say that it is happening at x equals negative 1. So I think it's the limit as x approaches negative 1. Is there an answer to this one? The limit as x approaches what equals negative infinity? Well, where is the function headed toward negative infinity? Well, okay, right here, yes. So can I say that it's the limit as x approaches 2? Nope. Because remember, this means that the left side and the right side match and are approaching infinity, negative infinity. It's just the left side. So here's what you can do, though. To answer the question, you would need to say, as x approaches 2 from the left. Super important. And is there another place where f approaches infinity? Yeah. I think it's at 2, but I think it's from the right. It's going toward positive infinity, but only from the right. Okay? And without the from the left or from the right, this would be incorrect. This would be an incorrect statement. But the top one is good, because both sides, left and right, are headed toward positive infinity. All right. Now, we're going to evaluate some limits, and we're not going to do, we can do Plan A, Plan B, Plan C from yesterday. Plan A, direct substitution. Plan B, try to use algebra on it. Well, good luck. It's 1 over x. There's nothing you can do. Rationalize the numerator. It's already rational. It's not going to work. So we're going to, conceptualize. We're going to use our brain. No steps. Use your brain, okay? So I've got them each written out. Now here's how I want you to think about this. This is going to get crazy. And you're going to find that I say things when I teach, and I'm saying them so that you understand them, but it's not necessarily good vocabulary to use on a standardized test like AP. Okay? Just keep that in mind as we do these problems. So, the limit as x approaches infinity of 1 over x. Well, let's try to plug in infinity into this problem. Okay, you can't plug in infinity. It's not a number that you can substitute in. But conceptually, think about it. As x goes to infinity, wouldn't x be getting huge? So, think about it this way. Isn't this kind of like 1 over a positive huge number? As x approaches positive infinity, so I'm plugging in infinity. So I'm thinking about, what if I plugged in some positive huge number? All right? And now, do that math in your head. What do you think you get if you grabbed your calculator and you did 1 divided by, 10 million? What type of answer would you get? I think you would get a tiny positive. Super tiny positive, right? How tiny? Well, I don't know. Well, dude, you plug in a bigger huge number. Because we're going to infinity. We can always keep going bigger and bigger. But plug in something bigger, it's going to be more tiny. So positive and teeny tiny. Think about how that would look like on a number line. I think we're getting close to 0. Does 1 divided by a huge number equal 0? No. 1 divided by a huge number gets close to 0. It's approaching. That's where it's headed. Remember, a limit isn't what does it equal at this number. It's as this gets close to this, where are my y's headed? They're headed towards 0. And on this one, okay, plug in negative infinity. So I can say that this is kind of like 1 over a negative huge number. 1 divided by a negative huge number. Well, my result is going to be negative, and it's going to be tiny. I'll get a bigger negative and a bigger negative and a bigger negative. I want to get a negative tiny and a negative tiny and tinier and tinier and tinier and tinier. They're negative, but they're they're so close to zero. They're approaching zero from like underneath zero. So I can say the y's are headed towards zero. The limit equals zero. Okay? So this is a concept that that I need you to be able to think through really quickly. 1 over a huge number, where is it headed? It's headed towards zero. 1 over a negative huge, where is it headed? It's headed towards zero. We're going to be doing that a lot. Now, okay, down here, the limit as x approaches infinity, I've got a quadratic over a quadratic. And we were hoping to cover limits in pre-cal last year, but with the crazy schedule, you can only teach 30 minutes a day, 3 days a week, and all that stuff. Whew, we didn't get to limits. But anyway, so I'm going to show you how to evaluate a limit. You've got a polynomial over a polynomial, and we're headed toward infinity. Well, here's something I kind of need to warn you about. This kind of looks like it might be. Do you know what 3x squared minus x minus 2 looks like when you graph it? I mean, kind of. You know it's a parabola that opens up, right? Okay. As x approaches infinity. So visualize your parabola. As x goes to infinity, where are your y's headed? They're headed toward infinity. So you might think that, hey, I can use those limit laws and I can split it up. Limit of the numerator, limit of the denominator. This one's headed toward infinity because I know what a parabola looks like. This one's headed toward infinity because I know what this parabola looks like. Kind of. I mean, it opens up. So if this is headed toward infinity, and this one's headed toward infinity, I must be able to cancel my infinities and say that it's approaching 1. Not the case. Not the case at all. And let me tell you why. It's true that this is heading toward infinity. It's true that this is headed toward infinity. But they're both headed toward their different infinities. Yep, this is some huge number. This is not the same huge number. Like if this were 8,000,000,004 over 8,000,000,004, yes, you could reduce them, but they're not. They're not the same number at the same time. So just because you're thinking something is headed toward infinity and something else is, that doesn't mean you can assume that they're the same infinity. Okay, so how are we going to do this? Well, we are going to look at, we're going to try to use some algebra on this and manipulate a little bit. So I'm going to look at my highest exponent, and my highest exponent is x squared. So here's what I'm going to do. I am going to multiply the numerator and the denominator by 1 over x squared. Highest degree, multiply, that's what I'm going to choose, multiply by that. And what's going to happen is I'm going to get some terms that look kind of like these. Okay? So if I multiply this polynomial, if I distribute here to here, I'm just going to get 3. If I distribute here to here, my x on top is going to cancel. I get 1 over x, right? And I get 2 over x squared. So this is what my new function looks like. You might need to pause the video and copy it, or wait until I'm finished. Pause the video and copy the whole problem. All right, so ready? Let's try to evaluate this. Using my limit laws from, I don't know, a few days ago, I can think of these as the limit as x approaches infinity of this, minus the limit as x approaches infinity of this, minus the limit as x approaches it, right? I'm not going to write it all out. We're just going to do this in our heads. So As x approaches infinity, what's the limit of 3? Just 3, it's a constant. As x approaches minus. As x approaches infinity, what's the limit of this? Well, think about it. 1 over huge. This is headed towards 0. Okay? It's not going to ever be 0. 0-ish. Good enough. And this one, 2 divided by huge squared, that's headed toward 0. And you don't have to write the ish. I just want to let you know it's never really going to be 0. It's never really going to be 3. Talk about that later. But it's headed towards 0, headed towards 0. Let's do the bottom. The limit of a constant is 5 plus. This is headed towards 0. This is headed towards 0. Where is this headed? It's headed toward 3/5. Is it ever going to get there? No. These are still going to be numbers. They're just going to be like super tiny number, super tiny number, super tiny number, super tiny number. But this whole fraction is getting close to 3/5. It's approaching 3/5. Now, look back at the original problem. Do you see a coincidence? You should. The answer to the limit turned out to be the fraction leading coefficient compared to leading coefficient. It's a shortcut that you're going to want to use it. We don't need to do this every time. But it works when you've got a polynomial over a polynomial, same degree. Same degree. If this were 3x cubed and this were 5x squared, the answer to your limit would not be 3/5. So it works when you're headed toward infinity and when you've got, or negative infinity, and you've got the polynomial with the same degree. Okay, next one. You are supposed to find horizontal and vertical asymptotes for this function. Now, I just went over horizontal asymptotes on the front page. Horizontal asymptotes, remember, we see horizontal asymptotes when we look toward infinity and when we look toward negative infinity. That's when we see horizontal asymptotes. So in order to find our horizontal asymptotes, I'm going to do that whole limit as x approaches infinity thing. But I want to see if there's a I want to see if there's a horizontal asymptote that way, and I want to see if there's a horizontal asymptote that way. So I'm going to do both the limit as x approaches positive infinity and the limit as x approaches negative infinity. And that'll tell me, does it level off anywhere? So here I go. I'm going to work on plugging in infinity. Now, think about this. Plug in infinity, square it, multiply by 2. You're going to get a pretty large number, right? Do you see how the plus 1 is kind of meaningless? You know, it's like the richest person in the world walks by a penny on the ground. Dirty penny, probably covered with COVID germs. Are they going to stop and pick it up? No. They've got enough money, they don't need the penny. Well, that's kind of this concept. This is so big. Infinity squared times 2, this is so big. Does the plus 1 really matter? Not really. Same down here. Plug in infinity. Ready? You got infinity times 3. Ooh, that's pretty big. Oh, now take away 5. Okay, so this, when we're looking toward infinity, the plus 1 and the minus 5 really don't mean much. So this is similar to the square root of 2x squared over 3x. Because the plus 1 and the minus 5, don't really mean anything. Now, square root this. So I've kind of got the square root of 2 times x over 3x. You can cancel out your x's. As x approaches positive infinity, this function is headed to whatever decimal this is, radical 2 divided by 3. That's where it's headed. Right? Because when you plug in positive infinity and then you square it, and then you square root it, you get x. Okay, let's do the negative infinity. This one is kind of tricky. So I can say, yeah, it's like, kind of like this. Okay, but hold on a minute. We are plugging in negative infinity. Okay? So when we plug in negative infinity, do you all agree with me that this right here is going to be negative? Gonna be negative. This one's going to be negative. What do you think about this one? So, plugged in negative infinity, squared it, got a positive result. Square rooted it and got a positive result. This one is going to be positive. This one is going to be negative. My answer to my limit is negative. And the tricky one happened when we were plugging in negative infinity. That's what you're going to have to be careful of. Okay, moving on. Vertical asymptote. Remember that I mentioned this in a previous video. When your denominator and your numerator is 0, that's the whole in your function. When it's just your denominator but not your numerator equaling 0, that's a vertical asymptote. So how do you find a vertical asymptote for this function? Totally easy. Find when your denominator is 0. My denominator is 0 when x is 5/3. Now hold on, quick check, head, mental math here. If I plugged in 5/3 to my numerator, would I get 0? Just double checking, making sure that's not a hole. If I plug in 5/3 to my numerator, would I get 0? No. What would I get? I don't know. I don't care. Wouldn't get 0. So yes, confirmed that is a vertical asymptote. Okay, moving right along. As x approaches infinity, where is this headed? Well, again, in huge number squared. It's so big. Do we even need the plus 1? I don't think so. So this is kind of like the square root of x squared minus x. This is just kind of, I'm writing it lightly. This is kind of my thought process, kind of like the square root of x minus x, and I square root that. This time, these are the same infinities. This is an x, this is an x. I'm plugging in the same huge number into each term. So the limit there is 0. Is it going to equal 0? No, because remember there's this plus 1 there, so it's not going to equal 0. It's just going to get super tiny as x approaches infinity. Oh, this is a good one. Here's what you need to know, really from this point on. You need to know approximately what e is, just kind of for reference. E is like 2.71-ish. It's irrational like pi, so it goes on forever. I have the 2.71 memorized. You need to know what the graph of e to the x looks like. The graph of e to the x looks like this. So in e to the x, as x gets huge, e to the x gets huge. Of course it does, right? 2.71 to a huge power is going to be a huge number. As x gets negative and small, e to the x gets super tiny, close to 0. Okay? So, let's do the limit as x approaches 0 from the left. Here's my thought process. You ready? It's kind of like e to the 1 over, let's see, what are we plugging in here? A number really close to 0 coming up from the left. So I think as x approaches 0 from the left, I think we're talking here about negative tiny numbers. Negative tiny numbers. Now, check out this exponent. What's happening here? Just the exponent, don't look at the e. 1 divided by a negative, tiny. My exponent is going to end up being a negative. 1 divided by super tiny. What is 1 divided by teeny, teeny, tiny? How many times does this teeny tiny number go into 1? A lot. It's huge. Your e to the x graph, what happens when your exponent is negative? Huge. Where are your y's headed? They're headed to 0. Next one, sine x. You should know what the graph of this looks like. Okay, that's a pitiful looking graph, but you know that it oscillates back and forth between 1 and negative 1. Look way out toward negative infinity. Where are my y's headed? What's it closing in on? It's not closing in on anything. It's bouncing back and forth. 1, negative 1, 1, negative 1, 1. So this limit doesn't exist. Getting there. Closing in on it. The limit as x approaches infinity of x cubed. Plug in a huge number and cube it. you get super huge, right? So I'll write super huge, super huge. But answer the question, okay? You're not going to write super huge on an AP exam. Where are the y's headed? They're headed toward positive infinity. As x approaches negative infinity, plug in a negative huge number and cube it. You get a negative super huge number. So negative infinity is where the y's are headed. Next one. As x approaches infinity, x squared minus x. So you're going to do huge squared minus the same huge. They're both an x. So huge squared minus huge. Well, square this. What do you get? You get super huge minus just huge. Subtract them. Describe your answer. I think you get another huge number. Right? Super huge minus just huge equals a huge number. Well, you might say, well, why wouldn't the limit be that exact number? Because whatever you plugged in to think this through, plug in something bigger. Plug in something bigger again. This is going to get even more big. The difference is just going to keep getting bigger and bigger and bigger. So my answer here is positive infinity. Okay. This is a good example. I'm not going to take the time to go through it. I really want to get to squeeze theorem with you. But I went ahead and filled it out in the notes. If you want to pause it, draw it, think it through. I went way back, first semester, first 9 weeks even, pre-cal, with multiplicity, whether it touches or crosses. I went back to, end behavior and stuff like that. So take a minute and go over that. I want to talk to you about squeeze theorem. This is pretty important. And before I do, let me just, I drew a really wacky picture. I drew a blue function, a pink function, and a green function. And do you think my statement up there is true? Is my green function always less than my pink function? And my pink function always less than my blue function? Some of you caught me. I think right here, because they all come together and touch, I think that I should say less than or equal to. Okay? I don't know what the pink one's doing, but I do know that it's being squeezed between. It's constantly being squeezed between these other two functions. So sometimes, like the blue one and the green one might be nice functions that you kind of know something about. And the pink one might be crazy. And you can say, I don't know anything about the pink one, but I know that the pink one always is between the green one and the blue one. That's the premise of the squeeze theorem. Now let's get into the details. The squeeze theorem works great with sine and cosine functions. Sine and cosine always are squeezed between positive 1 and negative 1. Okay? So, we are going to show, this is kind of like a proof. This is why I need to go over this with you in so much detail, because we're kind of doing a proof, sort of. I'm not going to make you do statements and reasons, but I am going to make you show me every step. You can't skip any steps if you're doing a proof. So we're going to prove that the limit of this crazy peak function is 0. The limit as x approaches 0 of the crazy peak function is 0. We're going to prove that. So here's where we typically start with these proofs. What do y'all know about sine of whatever? Sine of x squared, sine of 2x, sine of 8x. What do you know about your sine function? You know that your sine function is always trapped between -1 and +1. True? Okay. Now look at your peak function. Let's try to get this peak function in here somewhere, legally. So this is like our first fact that we know for sure. I know this, you know this. I know that you know this. It's a pretty easy fact. This is where we're going to start. So what would you like me to write on my next line when I squeeze this between -1 and +1? Look at the peak function. This is the fact that we know. What would you like me to put here? I think you would like me to put 1 over x. And because you know that the sine of anything is between -1 and +1, I'm comfortable with you making the statement that the sine of 1 over x has to be trapped between -1 and +1. Do you know what the graph of sine of 1 over x looks like? Not exactly. It's undergone some horizontal transformations. You don't really know what it looks like, but you know enough about trigonometry to know that this, whatever it looks like, it's trapped between -1 and +1. Okay, so do I now have my peak function right here? No. I have the trig portion, but I don't have this. I need you to legally get x squared in front of your trig function. Remember, you can't touch your angle. Do not touch this. Once I wrote it the first time, I am not touching this. But I can multiply this by x squared. As long as you multiply each side. Well, you got 3 sides now. You've got a left, you've got a middle, and you've got a right side. As long as you multiply each side by x squared, that's totally legal. So here's what you've just done. You started out knowing with your knowledge about trig functions, you said this trig function I know has to be between -1 and +1. Since you made that statement, you went on to say, oh, you know what, I need an x squared in front of there so that this matches my problem. So you multiply by x squared, multiply by x squared. So now you have this. I bet you didn't know that this peak function, right, you have no idea what that looks like. I bet you didn't know that this peak function was always trapped between this upside down parabola And this right side up forever. I bet you didn't know that. But you do now. How do you know that? Because you started with a fact that you knew and you legally built on it. Okay, so now we've got this true statement. Well, that's great, but I still need to do a limit on it. So you need to do a limit on this pink function. Do a limit on the pink function. Let's do the limit as x approaches 0 of my pink function. But guess what? If I do a limit on the middle piece, you have to do a limit on all three pieces. So I have to do a limit on this side, and I have to do a limit on this side. Now, I think you can evaluate this limit. As x approaches 0, where is this headed? It's headed towards 0. And I think you can evaluate this limit. As x heads towards 0, where is this headed? Towards 0. This limit that we were originally asked about is trapped between 0 and 0. Guess what the answer to it is? 0. So to finish up my proof, I would say, so by the squeeze theorem, the limit as x approaches 0 of x squared sine of 1 over x is equal to 0. And I'm not really going to circle that answer because really my answer was every single line. It was a proof. So we had to start out with some trig fact that I know that you know. Some people, they're like, oh, I got to use the squeeze theorem. I'm just going to set it up halfway through. And they'll start right here. I'll be like, oh, really? Oh, really? Okay, draw that function for me. Draw that function for me, because apparently you know what it looks like. And apparently you know that that function is always, see, no. You start with a fact that you know, and then you're going to build on it. So I started with a trig fact that I know, and then I legally, with algebra, built on it, and then I took the limit of all three pieces. I evaluated these two and said, well, by the squeeze theorem, this one has to be 0 as well. All right, so when you do your squeeze theorem homework, see, I don't know what this is going to look like. I don't know. My plan is to have a quiz that includes squeeze theorem on it. I would like to look at your squeeze theorem homework to make sure that your proof is good line by line, because some of you aren't used to showing every step. Some of you that you whizzed through pre-cal, you did all those My Math labs and never took out a piece of paper. Totally different in calculus. I'm going to be so picky about your work. So I need to see your squeeze theorem proofs before you take your quiz. Not sure what that's going to look like, but just make sure that you're not skipping any steps and doing it all the way through, okay? All right, good luck. That wraps it up.